I am Ria Chaudhary with the Catalyst Group. We're delighted to have you joining us today. We also have several other members from our team on the call. We have our CEO Clyde Payne and Vice President Alisa Davis joining us as well. Before we begin, just a quick reminders. Please stay muted unless you're speaking. Feel free to drop your questions in the chat throughout the presentation, and we'll address them at the end during the question answer round. And as always, since we have representatives from competing companies on the line, please keep in mind our antitrust guidelines. Let's keep the discussion focused on technology, research, and shared industry insights, avoiding any confidential business details such as pricing, production, or any customer information. Now let's turn to today's topic, which is industrial photocatalysis, electrifying chemical production. As industries accelerate their decarbonization efforts, photocatalysis is emerging as a powerful platform for electrified chemical processing. Today's session will provide an overview of industrial photocatalysis landscape, including key technologies, market potential, evolution from early stage research to commercial deployment. We will also explore reactor technologies with a focus on real-world scale-up and commercialization pathways. We're honored to have Dr. Suman Khatiwada, co-founder and CTO of Plasmonics, with us today. He leads the development of photocatalysis and electrified chemical reactors for decarbonized fuels and chemicals. He has helped raise over $100 million in funding and holds 47 patents worldwide. In today's talk, Dr. Khatiwada will share insights on technology development, scale up, and real world deployment, along with perspectives on where this space is moving. So with that, let's get started. Over to you, Suman.
Thank you, Ria. Thanks, Catalyst Group, for providing a platform for me to discuss this. It's good to see a couple of familiar names on the webinar here. And also hi to people who will be watching this recorded, I heard, over the next few days and whatnot. Here, I have my email address, suman@plasmonics.tech. So it's an open invitation for anyone who has questions, curiosities beyond this webinar. Please feel free to reach out directly, obviously. So with that, I think there is a Catalyst Group. Oh, the disclaimer is self-sufficient. Okay, all right. Let me quickly introduce my company with a Q on this slide. Company is Syzygy Plasmonics. We've been an operational company for about 8 years, 9 years founded. What we do is we have developed a new type of photoreactor technology, and are on this rubber meets the road moment where we're actually commercializing it and about to build a plant that takes biogas and makes jet fuel from it using a photoreactor technology. So that's us. There is a bunch of information in the slides, especially on the second half, where you'll learn a lot more about our company, and I'll be obviously more than happy to tackle any questions towards the end. I think we have a good 15, 20 or so minutes for Q&A if needed after I run through the presentations. So with that, let's get started. And again, thanks everyone for listening in live as well as on the recorded one later. When the Catalyst Group approached me, we're discussing titles, and we landed on this: industrial photocatalysis, from technology evolution to commercial photoelectric reactor. So it's basically what I briefly said. We're going to start with what photocatalysis is, its potential, why people have been excited about it for a few decades, and touch on why this hasn't become a commercial thing in those last 4 or 5 decades, and how at Syzygy we have unlocked a different type of photocatalysis and developed a different type of photoreactor to actually overcome those challenges and commercialize photocatalysis in chemicals, petrochemicals industry for real. So that's basically the outline of the talk. Disclaimers and trademark statements. here from the Catalyst Group. Yeah, so very basic slide I put together. Uh, you know, photocatalysis in its essence is a simple process in which the light energy activates a catalyst to drive chemical reactions. So we see the whole world is actually based on photocatalysis with energy coming from sun and plants using that energy from sun, CO2 from atmosphere, and absorb water from the soil to make glucose, which is a hydrocarbon, and that forms the basis of all life forms in our planet. So photocatalysis, photosynthesis in this case, is what the nature's been practicing since plants and animals uh, came to occupy this planet. So taking that cue from nature, artificial photocatalysis can also be done. It's been done. We've been doing it. What it means is using solar energy, photons from sun, or artificial light sources, and utilizing, chemically synthesized catalyst to take that energy from the sun to transform molecules from one form to the other. So, like again, taking cue from nature, that's what overall photocatalysis is. Go in. There you go. So talking about how the modern photocatalysis came to be, the first paper in the modern history was actually in 1972 by a couple of Japanese researchers, Honda and his graduate student Fujishima. Uh, they demonstrated first photocatalysis in and that was the first one that was published in literature. This is a landmark paper that started the field of modern photocatalysis. It established the foundational principles of semiconductor-based photocatalysis. I'll touch on that shortly. Uh, but this was landmark because it was first demonstration of sunlight-driven splitting of water uh, to to make hydrogen. So with that, it launched several decades and a few $1 billion of investments in R&D across many different research groups all around the world uh, in the last, what is that, 5 decades or so. Uh, uh, of photocatalysis research in here. So really a landmark discovery here. A few key points in terms of technology. Most of the photocatalysis that people hear about and practice, and most of the research that goes on is still based on this type of photocatalysis, which is semiconductor-based photocatalysis. In this process, you use a semiconductor material, very likely a titanium dioxide, TiO2, or a derivative of it, as a catalyst material, as the photocatalyst material to drive different chemical reactions. So when people talk about photocatalysis in chemistry, they usually refer to semiconductor-based photocatalysis, which is some transition metal oxide, usually driven by semiconductor physics overall. That is important because, I always get asked, what's different? Like people have been trying it for 5 decades, like how are you able to make it happen? And we'll get to that on the back end, but need to clearly establish that that's the case. With that said, maybe take a step back. Why people have been so excited about photocatalysis? Why has there been, decades of research and billions of dollars poured all around the world try to unlock commercialization of photocatalysis? Because it has a lot of promise, like from the get-go, right? Sun's out every day. So if you're able to use the energy from sun as your source of energy, it's likely to be the cheapest source of energy that you can have. And I choose my words carefully. It's likely to be all that, right? But that's the promise, right? If you're able to use sunlight as an infinite source of cost-effective, low-cost, cheap energy to make fuels, then you're likely to have a scenario where your fuels are, plentiful and cheap. Other aspects that actually has seen some commercial activity is environmental remediation. There's a few technologies that use UV light as well as direct sunlight for cleaning up of NOx and volatile organic compounds from air and as well as wastewater treatment. And that's again, if you're able to use photons and ideally solar, those become available to everyone and plentiful and ideally also cost effective. The one aspect that I have always been excited about and made me go on this journey of starting this company and developing this technology is the third bucket here in this slide, which is decarbonization potential. So if you're able to use solar to chemical conversion directly, then you probably don't have to rely on fossil fuel. That does two things. One, it you know reduces the reliance on fossil fuel, but the other thing is it also diversifies the pathway that you can actually make fuel with, and that should be a net positive for the world. But yeah, the one aspect that I'm really excited about and have gone a journey because of is this decarbonization potential, where and specifically focused on reducing carbon emissions from chemical manufacturing, petrochemical processing, uh, uh, and using photocatalysis to do it. The other aspect here on that second bullet point on the bottom I have is distributed fuel production, and that speaks to a few things. One is pure democratization, providing access to technology for everyone anywhere around the world. That has to be a good thing overall when it is not necessarily concentrated at one location somewhere. And the other aspect of that, as we are seeing with this, current global affairs, is potentially also going into energy security realm, where you have distributed fuel products and especially critical for places in the world which don't have native hydrocarbon resource available, and if they can use photocatalysis to make their own fuels at their own site, that has to be of importance, especially with all the global affairs that we're seeing. That might be an interesting aspect of where photocatalysis could come handy. With that, I mentioned about the challenges, why, like, if photocatalysis has this kind of potential, so much work been done, why has it not been commercialized yet? So this, I know it's a very heavy slide here, but I wanted to have all the summary in one slide with the uh, it's not the best marketing slide, if you will. The marketing gurus are not going to like it that much, but I wanted it all to be summarized in one slide. There are many different buckets that I put as a challenge on the left column here. Uh, I'm going to touch on each one of them because it is fairly important. Because whenever people are looking at photocatalysis, they are thinking about all this, and all these things are fairly warranted. Like these actually make sense. These were the reasons I saw when I was evaluating this photocatalyst technology that we ended up starting a company with and commercializing. These were the things I was looking myself on as the challenges to overcome for it to be successful, right? So let's go from top to bottom real quick. The first challenge is low solar efficiency. A couple of things there. The semiconductor-based photocatalysts, they usually work in the ultraviolet light part of the solar spectrum, which is a very small fraction of the solar spectrum. So you're not actually able to utilize all the photons of all the wavelengths that are coming in from the sun to your photocatalyst. So the overall efficiency is always going to be low because of that. Uh, the second point within that is, fairly obvious, is sunlight is not available at all times of the day. It is not the same at different parts of the world. You go from north to south, things change drastically. The weather patterns, the climate patterns are different from one place to the other. So when you're looking at building a chemical plant, your economics go really down because you're not able to have high utilization of your plant. Then you have to do other things to preserve that solar energy somehow that you can use it during the night, etc. So your plant utilization is very low, and anybody who's built a techno-economic model for building a chemical plant would know that that translates into very bad economics. So that's at the high level from solar. The the next few points actually have to do with the science behind how the semiconductor-based photocatalysis works. Uh, so a few key points here is whenever you increase photon flux, like you provide a lot of energy, you pump in a lot of energy, which means you're pumping a lot of photons. You're trying to like accelerate the chemical reaction, make it more. But because of semiconductor physics involved, it actually reduces the catalyst efficiency when you're increasing the photon flux. So you cannot make a very energy dense photoreactor with the semiconductor-based process. And along the same lines, these kind of materials also suffer from this thing called photocorrosion. They start to get corroded. They get surface poisoning depending on what kind of materials they are working with. And a lot of the times, because they are fabricated in a fab lab type of a setting, making thin films, uh, varying photon flux and temperature that photon flux varies also reduces the structural instability. But as we know, when you're building a plant, you're looking for your reactors uh, uh, reactors and the catalyst system to operate for thousands of hours, a few years before they can be replaced turnaround. And if you can't do that, if you have to replace them more frequently, the economics are bad. If you think some product selectivity, that's been a main theme on the CO2 molecule side on photocatalysis. A lot of issues with selectivity, lots of issues with reactor design. Uh, you know, Everything that I just spoke about, but also on top of that, uh, uh, whenever you increase the thickness of a thin film, trying to increase the surface and volume aspects of your chemical reactor, you actually start attenuating UV photons as the thickness of the thin film increases, and that creates these hot spots and temperature irregularities on those thin films, and that makes it not possible for you to have thicker films overall in your semiconductor-based photoreactor, and that limits the scale up. What it means is you need to have your chemical reactor similar to how you have your solar panels. Like you need to have acres of field to make few kilograms, few unit volumes of your molecules. So because of that, the economics don't work out. And the last point here has to do with the business side. If you're bringing in a new technology in chemicals and petrochemical industry, you have to compete with incumbent technologies. You have to make sense on price. You have to make sense on every aspect of the value proposition. Yours has to be better than the status quo. And because of all these issues mentioned above, cost competitiveness uh, is a big issue for conventional photocatalysis. So because of all these reasons and all these decades of research, photocatalysis has not been commercialized at scales as its promise and potential has suggested. So I said a lot of things here, and a lot of the times this kind of summary might be new for a lot of folks. So I'm expecting a heated, no, not heated, passionate conversation on why this and why us when we open the floor for Q&A. So with that said, here's the slide that introduces, our type of photocatalysis. So what is Syzygy Plasmonics commercializing? This is based on Antenna-Reactor photocatalyst. So this was invented at Rice University. The first paper published on this was in 2016. And the big hallmark of this technology is it is not semiconductor based. It is based on transition metal and their oxides. It is not dictated by semiconductor physics. So because of that, almost all the challenges that we spoke about earlier actually does not impact our type of catalyst. But when this was published, it was some experiment was done in the laboratory, but the a photoreactor that would be able to use this kind of catalyst and take advantage of its unique properties was not developed, and that's what Syzygy Plasmonics was formed to build and commercialize. So with this catalyst, uh, there in principle there's two nanoparticle materials. One type of nanoparticle is the antenna, which is a light harvester. The other part of material is the reactor, which helps with catalysis. So the antenna, the light harvesting type nanoparticle, is made out of either aluminum, copper, silver, or gold, and they are good plasmonic materials. That's why they make for a good light harvesting materials. And we can deep dive into plasmonic materials later if needed. Uh, and the reactor part of materials could be any transition metals or their oxide. The picture here in the center is a TEM image of a antenna-reactor photocatalyst. This one is an aluminum antenna with palladium islands, nano islands on them. That is the aluminum palladium system. On the right side of this slide, you see a library of aluminum family of our antenna reactor catalyst. I say family because the reactor part, the catalytic materials are, as you can see here, iron, cobalt, nickel, and other platinum group metals. This is to demonstrate that this is not just an idea, but these are actual catalyst materials that were formed and published in one of the publications. So similarly, we have developed copper, silver, and gold family of antenna reactor photocatalysts, and all these photocatalysts are good for many different types of chemical reactions. And I have a slide later on to talk about what that is. Quickly drawing contrast with semiconductor-based catalyst, thematically at least. As you can see here with antenna reactor, there are separate nanoparticles that harvest light and do catalysis. So the plasmonic materials are really good at harvesting energy from light. It is actually when you provide proper resonance with the photons and the plasmons, it is 100% transfer of energy. And then there are separate separate particles that partake in chemical reactions. And those are conventionally well-known good catalyst materials. In the semiconductor-based photocatalyst, the light harvester as well as the catalyst particle is the same material, usually the same material. And if it is not, it is just used as an additive. Like there's plasmonic material added, titanium dioxide based catalyst, but it's not the same as they are, that they are arranged in at the quantum level as hierarchical nanoparticles like ours. So that big difference on how the materials of construction are picked is the big difference on how our type of photocatalysis antenna reactor is different from convention. Few key notes here. The Professor Naomi Halas and Peter Norlander were the inventors of the technology, and so was Dr. Hossein Robotzazi. He was a PhD student in their lab. He's now our VP of research. We to the day have really good collaboration with Rice University. A lot of projects that we do together with them, and in the earliest days of our company, these three folks named here were instrumental in helping us, take it out of their laboratory and actually do the development of this catalyst photoreactor system. This is just to show to everyone as I said here, the first paper was published in 2016. That's way on the top. Since then, this has been published in Nature or Science 7 times. So the main purpose of showing this is twofold. One, it is we've been highly published, but all of it is new. We are at the bleeding edge of this new type of science. That's why a lot of people, especially when we started the company in 2018, 2017, 2018, a lot of people hadn't heard about it, but us together with Rice professors have continued to work on many different aspects of this and been publishing it in high impact journals like Nature and Science all over, and continue to do it to this day. As you can see, the last publication was 2025. We recently submitted another paper last week, actually, on Friday, for a new publication. So we continue to publish overall in terms of our own growth, etc. Like there, a lot of these are for many different types of chemical reactions. They have different types of catalyst. Early on, work was a lot of focus on platinum group metals. The later works are focused on replacing those platinum group metals in catalyst, in our catalyst composition, to using things like iron and nickel. As we learn how to, as we've understood the system better, as we've gone through a lot of R&D and all that. With that, I'm going to go to this slide. Put this slide together to help everybody understand how antenna-reactor type photocatalyst actually works. So I'm going to spend a little bit of time here talking about that. I'll focus on the bottom half of the slide first, and then I'll go to those 4 bullet points up last. So yeah, so it is a photocatalyst, right? So we need a light source. So we always have to have a source of photons that we obviously tailor to the needs of the catalysis that needs to happen, as well as the catalyst that is used. At the surface of the catalyst level and underneath it at the quantum level, there are actually 3 things that are happening in this type of catalysis. 2 of them has to do with photocatalysis, and 1 of them actually has to do with thermal catalysis. So the 2 photo ones are bunched in together here. I have named them photochemistry and photodesorption. So what happens is, as the energy from photons comes and is incident on the surface of the catalyst, there is this collection of electrons on the surface of the metal and metal oxides of the catalyst. That collective oscillation of electrons on the surface of the metal is called a plasmon, and it is always oscillating at a particular frequency. So when you mate that with the photons coming through, there is that transfer of energy that happens. So you put the energy from photons and the electron cloud, the plasmons are now able to energize themselves and create these hot electrons, which are just high energy electrons. Those electrons directly interact with molecules that are in the surrounding, which would be the feed molecules, and participate in making and breaking bonds. So direct photochemistry happens. The other thing that happens is these electrons participate in active desorption of molecules and intermediates that are formed during catalysis. This photon-electron interaction phenomena happens in the femtosecond scale, which is 10 to the negative 15 seconds. Catalysis happens in the picosecond scale, which is 10 to the negative 12. So this photochemistry and photodesorption is happening at a much faster, 3 orders of magnitude, faster time scale than catalysis is happening. So because of that, we see a few benefits. One is the catalyst surface is always available for catalysis, because there is not a binding of intermediates, especially on the surface of the catalyst, because the high energy electrons are always actively cleaning the surface out. Because of that, we see extremely high turnover frequency. So we don't need to use a lot of catalyst to do a lot of work, because our turnover frequencies are really high. If you see our paper on dry methane reforming from Nature Catalysis in 2020, you'll see that we've laid out how the turnover frequency of the catalyst is 34 per second. When you think about industry, you're talking about, nickel-based catalyst in a steam methane reforming, you're talking about, 1 per second turnover frequency. So because of that, we see, because of these photochemistry and photodesorption, we see extremely high turnover frequency. Because of that, we also don't see coking happening. We operate in a temperature regime which does not facilitate it anyway, but also that active photodesorption does not allow for carbon species in a particular reaction, or nitrogen species in other type of reaction to actually interact with the catalyst surface. And because of those, also we see new reaction pathways. So uh, delta H per chemical reaction remains the same, obviously, but the rate limiting steps might change. Because a lot of the times this binding energy that is needed for desorption is not the rate limiting factor in our process, and that changes the reaction pathways. So the intermediates form, the selectivities, all that can be tuned by understanding the what light sources you're using, what the characteristics of the catalyst material is, and what kind of chemical reaction that you're doing. Overall, we can tune in the selectivity, get very high turnover frequencies, extremely high reaction rates, and not see things like coking overall. And that's where the photo comes into play. The third thing that is happening is local heating. So as you can imagine, when you know have an intense source of light on a metal surface, that metal surface gets hot, right? A lot of kids, killing ants with the small microscopes and all that is same phenomena. So whenever these plasmons, high energy plasmons, don't interact with the molecules, because electrons are much smaller than the molecules and molecule species, right? They actually thermalize the crystal lattice of the catalyst and actually heat the thing up, heat the catalyst up. What we found over the course of development, this was a later learning for us as we were scaling up our photoreactors, is this is actually really beneficial for endothermic reactions, and our go-to-market processes are actually all highly endothermic. So by understanding that for these endothermic reactions, allowing the catalyst bed to heat up a little bit is actually helping with increased reaction rates, we're able to create a highly efficient photoreactor later on. So working principle, there's photochemistry happening, and local heating, thermal chemistry also happening. And overall, this creates new ways of doing chemical reactions that creates new type of value propositions for this type of photocatalysis, and has added benefit for endothermic processes. So now onto the bullet points here. I have the 4 points. This type of photocatalysis works with UV, visible, or IR light energy. We're not dependent on semiconductor physics. That helps. We use metallic nanoparticles. We use both plasmonically active, so good at harvesting light, and we use transition metals, which are good at doing catalysis. We're not affected by semiconductor physics, so we don't see photocorrosion and similar other things. Also, this allows for us to create a plug flow reactor, and that is actually huge, because most of the modern day, I say most, like in a lot of the modern chemical plants are built around plug flow reactors. So our type of photoreactor benefits from scalability of plug flow reactors, as well as high throughput and efficiency of the plug flow reactors overall. With that, just comparison chart on the left is the best performing photocatalysis based on semiconductors from Nature from 2016. You can see here there's a slow degradation of the performance of the catalyst as it goes through in a few hours. On the right is from our Nature Energy paper on the Antenna-Reactor photocatalyst. We use the same catalyst to do photocatalysis, and then thermocatalysis. Even with our catalyst, we see slow decline, and it's mainly because of coke formation when you're using thermocatalysis only. but while using photocatalysis, we maintain a constant methane reaction rate and selectivity on formation of syngas overall. So we have, by virtue of the characteristics of this new type of photocatalyst, we have successfully overcome all the challenges that have prohibited conventional semiconductor-based photocatalysis to be commercial. So with that, here's the cool part of the presentation. If it's not cool already, everyone meet the Rigel reactor. So Rigel is a photoreactor we have built at Syzygy over the last few years of development to go and commercialize this kind of photocatalysis. In essence, it is a fully electric chemical reactor. We use light sources, a lighthouse, literally a giant light bulb, a 200 kilowatt light bulb, is inside this reactor, and we use renewable power to provide energy to that light bulb, and that photon from that lighthouse goes on and provides energy to the Antenna-Reactor photocatalyst to do work. It's fully electric, so it does not have a smokestack, right? We don't have burner management system. We don't have to burn fuel to do chemical reactions. So plants built with our process won't have smokestacks. They might have a flare unit on the back for safety purposes, but they won't have an active smokestack. So if the electricity used has very low carbon intensity and the feedstock has low carbon intensity, then the produced chemical will have an extremely low carbon intensity associated with it. Other things, we don't use things like Hasselblad. We can build, we do build our thing with aluminum, glass, and steel. Like those are the three dominant materials that goes into the Rigel reactor, which helps with the unit economics of our modular system, obviously. The other thing is we can control its performance, turn down, turn up, start up, shut down, just like you control LED lights in your house. So if we are seeing some issue or we need to be responsive to a grid because there's brownout in the area and the local grid authority is like, hey, help us out, we could actually do all of that within a few minutes. Take the turn up and turn down, with extremely high responsiveness. We'll also talk about energy efficiency in the next slide. We're going to talk about the development. We've run this for about 6,300 hours or so now, most of it at our the demo plant that we have in Pearland, Texas, here right outside of Houston. We've completed multiple field trials, and we just received 2 weeks ago a report after a month and a half of work by a world-renowned technology licensor. They evaluated the technology to be TRL 8 and ready for commercialization recently. I won't be able to name them, obviously, because I'm bound by confidentiality, but more than happy to share that under an NDA with folks. So what I'm trying to showcase here with this slide is we built it. This thing is about 6 foot tall, slightly taller than me, actually more than a foot taller than me. And we've tested it for a long time. We have had people from outside, like industry experts, assess its readiness level. They have assessed it to be very high and ready for commercialization. And it has the capabilities that you can't have with a lot of different types of chemical reactors. Maybe a quick aside here. I said earlier that this is a plug flow reactor, so we get that advantage of being a plug flow reactor, but we also have a lot of advantages that make things like electrolysis attractive, because we are also a fully electric chemical reactor. So for us, we actually do get to have the best of both worlds with this technology. This slide, again, a little bit busy for a webinar, but this shows the history of development of our photoreactor within our company. The metrics we picked here are energy efficiency, hydrogen production, that's mainly for ammonia cracking to hydrogen, and the TRL levels here stops at 2024. So we started with extremely high, extremely low energy efficiency. At that time we're just trying to replicate the work that was done at Rice University Labs and evaluate if science and Mother Nature will allow us to actually make this happen. When it looked good, that's when we started fundraising. We also won a few government grants. We won an ARPA-E project and a couple of different SBIR grants that funded multiple different process pathways. We started taking ammonia to hydrogen process, trimethylene reforming that has now become our biogas to SAF process, as well as SMR, steam methane reforming. Those three were funded by different sources for us to scale up and develop this. So by the time 2024 came around, we were doing our field trial at Lotte Chemical in Ulsan, South Korea. There's a press release out there with the outcomes of this field trial from early, I think January 2024 or something similar. But in that field trial, we were able to demonstrate for ammonia e-cracking and energy efficiency at the reactor level to be 81%. And that is LHV of hydrogen produced in the numerator divided by the sum of energy in ammonia input plus joules of electricity used in the process. So very like an energy out versus energy in, very straightforward energy efficiency numbers. So this tells you that the process is extremely efficient, and in doing so, we also were able to actually scale it up from a few milligrams of hydrogen a day to close to 300 kilograms of hydrogen produced from one day. For the biogas to SAF pathway, this translates to 1.5 tons of syngas produced per day at an output ratio of 2:1. This is, there's a lot here. I'm not going to go through this slide in detail, but the headline is what I wanted everyone to take away here is we have incorporated simulation and modeling into our work from day one of our company. Professor Nordlander, so Professor Hallas is the experimentalist and Professor Nordlander is the theorist. So with his help, we've always developed a sophisticated modeling and simulation work, and that in conjunction with experimental work has been the reason why we've been able to understand this unusual phenomena, which is not understood before this came about, which is not in that yellow reactor engineering book that everybody studies and all that. So we have had to create our own way of grabbing that intuition, understanding the science, and actually developing something that nobody has developed before. And this has been a key part and remains to the day. At the Rigel photoreactor level, we have our model in about 90% agreement with our model overall, and that is just simply phenomenal. Just that would be published in a high impact journal, but that's our trade secret, and we keep it inside, obviously. So now more on commercialization and our R&D. Again, a little bit of busy slide, but this encapsulates the process pathways that we have ready for commercialization, as well as mentions a few chemical reactions here that we are actively doing R&D on, and those form our product pipeline, basically. So up top here, biogas to SAF, it's actually biogas to syngas, and then you use gas to liquid technology on the back end to take that syngas to SAF or methanol or diesel or whatever that hydrocarbon liquid molecule of choice is on the back. So that is ready, and we'll touch on that. That's been the one that we published press releases on recently, etc. That's the first one. The third one there is almost the same exact thing, but doing SMR. The same plant can do both, same catalyst, all of that, but we can do just plain steam methane reforming, do the same process. The second one in there is ammonia e-cracking to hydrogen. This is what we were mainly known for, Syzygy as a company, until about a year and a half ago. We have the world's best performing ammonia cracking system, and I will be more than happy to be challenged on why that is the case, obviously, outside of this forum. But the market is not there. People are not importing green ammonia in droves and making hydrogen on site at a different place to use it. It had a lot of promise, but it simply didn't has not materialized yet. But us being a platform technology, we've been able to focus our energy squarely on the market that exists, which is sustainable aviation fuel, and are therefore taking biogas to syngas to SAF pathway as our go-to-market work. And the subsequent slides are going to be touching on that, obviously. The earlier stage reactions in development on the bottom are near and dear to us also. Obviously, we have an active, fully electric ammonia synthesis process using our photoreactor knowledge, photocatalysis knowledge on ammonia synthesis. That is an ARPA-E funded project. We are in second quarter of that project, recently started. We have a corporate sponsor funded project to make butadiene from ethanol. We have recently been really interested on naphtha reforming to syngas because as we are building a SAF plant, a cut of of that plant is naphtha, and the economics of the plant looks good if we are able to reform on site that naphtha back into syngas, so we can make so the plant makes all SAF on the back end. So we have that actively going. We can do reverse water gas shift with the same process as number 1 and 3 up here. We also have interest on ethanol to ethylene, and we are also uniquely capable of directly splitting H2S. That project is not active, but really important to us for our future pathways because with that we can directly split H2S to hydrogen and sulfur, and that would be to replace Klaus process in refineries, still producing sulfur, but it makes it a hydrogen producing reaction. So that should have a lot of benefits for future refineries. So this slide is a snapshot of what we're working on, what we're taking to market, and what are the processes that we are working in the background as our pipeline to product pipeline to bring in the future. We started this company to electrify chemicals and petrochemical industry, and by doing all these things is how we actually achieve that. Brief note here on our field trials. We did our biogas to syngas field trial at RTI in Raleigh, North Carolina. This is the first time we put multiple of our photoreactors, tied it to a pilot scale FT Fischer-Tropsch system, and made liquid fuel out of that. The project was sponsored by BP, Equinor, and Sumitomo. All are now investors in our company. The second one, which was the Rigel photoreactor testing, was done by Lotte Chemical in Ulsan, South Korea. Sponsors were Lotte and Sumitomo on that project. And the third one on the right is our pictures from our own industrial scale demonstration plant we have in Pearland, Texas, where we continue to run the plant. There are actually 3 different plants in there. One is a pilot scale, smaller reactor testing. The other 2 are Rigel reactor, commercial reactor scale testing, one for ammonia cracking, the other one for carbon-based reactions. You see the photo of the unit with the silver metal top. That is of the carbon based plant here. Anybody interested to come visit, we're very open to showing our stuff to people. Reach out with obviously let me know why you want to see it. If we're good, I will be more than happy to put you in some fire retardant clothing and have you walk the plant, see our control room, interact with our operators and our industrial engineers who work around there. And yeah, we're only about 20 minutes or so from downtown Houston, so fairly easy to get to. This is where we've been doing thousands of hours of testing the plant itself is built with a PLC system, and the control room is actually remote on the inside. Also on site, we have a fully integrated semi-automated catalyst manufacturing plant. So we build our plant on site, we assemble our reactor on site, as well as test it on site. So we have control over the speed and learnings all around within our own facility. So quickly on that biogas to SAF pathway that we are taking to market, and I think with that I'm going to actually accelerate and try to finish it in 3 minutes so people actually have time for questions. I forgot about the time, I just saw it. Anyway, this is what we're taking to market. Take biogas combined with steam, use Rigel, make syngas of a 2:1 ratio, and tie it into gas to liquid technologies, Fischer-Tropsch, and then hydrocracking that makes the SAF cut. This SAF is meant to replace fossil-derived jet fuel. It has 90% lower carbon emissions. It is probably most importantly compliant to the mandates in UK and Europe, RFNBO and EU RED, that qualifies them, that allows it to be to demand a premium price over jet fuel, and also there are several advantages over other SAF pathways, including cost. This process, this one keynote here, why us? Not because it is a cool technology, but because we are doing dry methane reforming, we're able to use both methane and CO2 molecules as feed to make the hydrocarbon fuel. If you're using SMR, you're mainly using the CH4 molecule, so you're not using about 40 to 45% of the molecules in the biogas. So the yield, when you compare with us with SMR, is actually much lower for them. Same thing with electrolysis. You'll have to remove methane molecule from biogas only using CO2, so your yield when you compare to us is low. So if you're an asset owner of a biogas, you want to work with our technology because for the same asset, you end up making more SAF, more high value fuel. We're building our first plant called NovaSAF 1 in Uruguay at a dairy farm where we take cow poop, take the cow poop to a biodigester, make biogas, and then take that biogas and make jet fuel from it. We also have multiple other projects lined up where we're working with landfills, sugarcane waste at sugar factories to build global scale plant beyond NovaSAF 1 currently. And it's the last slide. This is the plant that is ready to be built. We are FID ready. Currently fundraising for the company to be able to build the plant. Just started it actually a couple of weeks ago. And here's my contact. So yeah, I went a little long, but it was very descriptive, and I hope I answered a lot of questions that people had not naturally. And I actually can stay longer if other people are willing and if needed. But yeah, with that, hand it over to Ria.
Thank you so much, Suman, for the excellent presentation, and thank you for accelerating in the last 5 minutes. We'll now open it up for question answers. There are some questions in the chat, but if you have any other questions, please feel free to drop them in the chat or raise your hand and we'll unmute you. So the first question is, does antenna signify the arrangement of metals over alumina surface?
We have to, so each catalyst is designed in a very unique way. So yeah, so the distribution, the size of the reactive catalyst material, the crystal structure of it, is it alloyed or is it present as an island? All those things matter. So we actually design it at in some cases as single dispersed atoms of different units within the molecule, and that is actually not alumina surface. That ball that we looked at, that's actually aluminum nanoparticle. And we do use other things in our catalyst to make it commercially viable, like supports and stuff, but it is not an active part of the catalyst.
Thank you. The next question is, please provide the typical operating conditions of the Rigel photoreactor, temperature, pressure ranges, etc.
So I will not do that in the general forum. Overall, I apologize. I need to be conscious of our intellectual properties,
Sure.
but I will leave you with a few things. Uh, the inside of our reactor has light sources. They cannot handle a lot of high temperatures. The body that they sit in is made out of aluminum. Uh, so there you go. And we don't use any, high alloy, high alloy, high nickel alloys like Hastelloys, etc. and all that. We don't use that. The other thing is we actually, for these endothermic reactions, actually have pushed uh, the temperature of the process gas exiting from our reactor to be higher and as high as possible. Mainly because as we started designing the plant, we realized that the higher temperature allows for a higher quality and quantity of heat in the process gas, which enables better heat integration in the plant. That makes the plant more efficient. So actually having lower temperature, low grade heat in process gas coming out is actually not that useful. So I'm
Hmm.
gonna pause right there.
Okay, thank you. And people can have separate conversations with someone and reach out to him directly if they have any follow-ups.
Yeah.
The next question is, what are the biggest commercial challenges you're facing on these projects?
So today is we just need to we're in a spot where we feel really good about everything. Engineering of the plant is complete. An EPC has wrapped it around. Our licensor partners have done their work. It's right now just funding, right? We're building a first of a kind plant. So that appetite for people to, despite all the awesomeness that I showed you,
Mhm.
appetite for it's not everyone's appetite to help build a first of a kind plant. So that is literally the big one. And then immediately after that would be execution part. We have assembled a great team internally as well as partners uh, for the first plant and continue to do so for this plants number 2, 3, and 4. But plan is one thing, we have to execute, so we're always going to have that thing in there. But not worried about technology, not worried about integration, worried about funding and execution. No.
Sure. Yeah, thank you. Um, the next question is, picking one application example, syngas to SAF, what are typical conversion X selectivity is equal to yield? And does this require recycle per pass?
Yeah, so we do have recycle stuff because we have the FT unit and then the hypercracking unit. So there's recycle coming from many different places. So yeah, so there's a steady, there's a startup mode, and then immediately a few hours after, the plant goes into the steady state, which is on a recycle mode. Overall, yeah, so one pass, I think for the first plant, we're looking at around 81% carbon uses in the first plant. It is smaller. In the second plant that we've already started designing the process model for, we're looking at 95% carbon utilization.
Okay, thank you. I guess the last question in the chat is, do the higher turnover frequency impact catalyst lifetime and regeneration?
It doesn't. What affects is sulfur content in the feedstock. So we have to keep the incoming feed gas clean of sulfur. It also does not, like every other catalyst, is the same thing. It doesn't like solid particulates coming in. So in our biogas to SAF pathway, we have to knock out things like siloxanes and keep sulfur out. We don't see anything in sintering because we're not operating at those temperatures. We don't see coking, as I mentioned earlier. Uh, we actually have not been able to kill our catalyst outside of those things. But in our models, our techno-economic models and financial model, we do say we'll change the catalyst out every 3 years. But that is just to keep everyone happy and focus on the right conversation. We actually haven't been able to kill our catalyst outside of sulfur.
Okay, yeah, good to know. Thank you. Um, that's all the questions. Thank you, Suman, for an insightful and engaging presentation. And thank you, everyone, for joining us and for your thoughtful questions. We really appreciate your time and participation. If you have any follow up questions, please reach out to someone directly or you can reach out to us. And the recording of this presentation will be sent out to all our members. Yeah, look forward to seeing you in our upcoming sessions. Have a good rest of the day, guys. Thank you. Thank you so
Thank you,
much.
everyone. Bye.